Hi everyone, this is the cell membrane review and cell transport notes. So as a reminder, here is the phospholipid bilayer, also known as the plasma membrane, also known as the cell membrane. The phospholipid bilayer name comes from the little small phospholipids, and there are two layers of them. The tails are hydrophobic and they point together. Um, and the heads are hydrophilic, they are polar, so they are able to touch the water. Um, and so we have certain channels that allow polar molecules to travel through the membrane without going through the no-go zone. We also have these other important parts of the membrane, the glycolipids, which have the carbohydrate chains. We have the integral proteins, which are going to be the ones that span the entire periphery, I'm sorry, the entire span of the cell membrane. The peripheral or periphery membranes, sorry, proteins are going to be the ones that are only on one side of the cell membrane. The different parts I already went over here, and the cell membrane is described to be as semi-permeable. This means it only is allowing certain things in and out. It's very selective, so it keeps the bad stuff out and the good stuff in, for the most part. It needs to be flexible, so it's not a wall, and it helps maintain homeostasis. The two main types of transport that I spoke about, or I will be talking about here today, is passive versus active transport. I did talk about diffusion, the movement of particles from high to low across the membrane. So if you count these particles here versus these, you notice that the movement of particles is going from a high concentration to a low concentration. And they are passing through the membrane without any help. We call that diffusion. It's a form of passive transport. Passive meaning not needing any type of energy. The facilitated diffusion examples are here. So we have the triangles moving across requiring no energy because they're going from high to low. However, they do require the aid of a um, channel protein here versus a carrier protein. A carrier protein will have a like modified shape here to accommodate the particles as they move across. So both of those are considered facilitated diffusion, which means you are helping the diffusion process. You cannot cross on your own. All of those are going to be a form of passive transport, which means no energy required. The next type is going to be active transport. Active transport is when you have particles moving from low concentration to high concentration. So we see the diamonds here. Okay, so that is going to be the particle we're watching here. And as we notice, the particles are moving from low to high. So we need to use ATP energy to activate or power this pump. We call an ATP protein pump. So the point of diffusion, um, and ultimately just anything moving across the membrane, going from high to low concentration, is that over time, you will see a equilibrium met. So if you can see here, all my particles are on the outside here of the cell we call the extracellular fluid. And over time, they are diffusing across the membrane. And they're not diffusing across so that all of them cross the other side per se, but they are diffusing across from high to low so that they can reach equilibrium. So the word equilibrium means the same on both sides. Okay, and that's what we want to achieve here. So, here are the different types of transport, the specifics about them, movement of particles, energy required, all these things. So let's go ahead and start this chart. So type of transport is passive. It's either diffusion or osmosis. So I didn't talk about osmosis yet, but I will. And the movement of particles are from high to low for diffusion. Osmosis is the movement of water from high to low. So don't be confused there. Movement of particles is diffusion, and movement of water is osmosis from high to low. Both high to low, but it's just a matter of what is moving. Diffusion is a movement of particles or solute from high to low concentration, and osmosis is the movement of water from high to low concentration. No energy required because it's passive. Any extra information here that we need? Let me think. I don't think so for this one. Facilitated diffusion means the particles are moving from high to low again. Okay, so that's either going to be a channel protein or a carrier protein. Okay, either way, they both work and no energy required on that one. Lastly, active transport is like an ATP powered pump. Okay, and we are moving from low to high concentration, and we do need energy required. Okay, next section is the factors that affect the rate of diffusion or how fast the particles will diffuse. So if we think about this conceptually, if we increase the temperature, let's say we want to boil the substance and make it diffuse faster. If we boil it and increase the temperature, so let's say let's boil the water or just increase how hot it is, the rate of diffusion is going to go up. It's going to diffuse faster. We are going to increase the rate of diffusion. So it's going to diffuse faster and reach equilibrium faster. If we decrease the temperature, that's this box here. If we decrease the temperature, we're going to decrease the rate of diffusion. Okay, so if we make it colder, okay, we make the water colder that it's diffusing in, whatnot, it's going to decrease the rate of diffusion. Now, let's talk about the size of the particle. So, as the particle size gets larger, okay, and it's trying to diffuse, it's going to decrease the rate of diffusion because the particle is just far too big. On the flip side, if we decrease the size of the particles, we have really small particles crossing the membrane. They are going to diffuse much faster. Okay, so this one is a um, inverse relationship. So if we go ahead and notice here, increased temperature, we increase the rate of diffusion. Now, if we increase the size of the particle, we're actually decreasing the rate of diffusion. Okay, so that's going to be an inverse relationship versus temperature is going to be direct. And lastly, we have the concentration of particles or how potent it is. So if we have a substance that's very potent, it's going to increase the rate of diffusion because there's going to be a lot of that substance going from high to low. And so if there is a high amount of that substance, the concentration going from high to low, it's going to increase the rate. So back to our direct relationship like temperature. All right. Moving on, I did mention osmosis a little bit in the previous table. Osmosis is the movement of water from high concentration to low concentration of water, not of solute. So this is like the egg lab. So we're going to talk about the egg lab. The egg lab, we are putting the egg in certain different concentrations of different types of solutions, and you're seeing the effects of that on the egg size. And so this is because the water is moving either into the egg or out of the egg. If this picture shows osmosis as well, you see the selectively permeable membrane splitting the beaker, and we have a sugar solution on the left side. And if it's a sugar solution that's concentrated, that means water is less concentrated there. And on the right side, we have a more dilute sugar solution where the water is more concentrated. So water is going to move from a high concentration to a low concentration. So eventually, if you let it, play out, the water is going to move to the left side of the beaker where there is less water there because it looks like there's the same amount of water, hypothetically to start. But if you let it move, if you let the semi-permeable membrane do its job, the water is going to move towards the side of the beaker that has less water. So high to less water or low water is going to see this movement to the left. Okay. If you need more help on that, please ask your instructor. Types of solutions is next. So basically, we need to go over some vocabulary. I already mentioned the word solute. That means particles. So a solid that dissolves in a liquid is called a solute. So for example, in our picture, we have salt plus water makes salt water. So the salt is the solute, okay? The solvent is going to be the water itself. It does the dissolving, aka water. Water is the universal solvent on this planet. And together they make a solution. So a solute plus a solvent makes a solution. All right. So when making lemonade, what is the solute and what is the solvent? So we're talking about the lemonade you make from the store-bought powder. So like, I don't know, pink lemonade. How would you make that? Based on the words, vocab words here. What is the solute and what is the solvent? So go ahead and write them right here, please. Is it going to be the powder, the water, or the lemonade mixture itself? Okay, let's move on. So types of solutions here. We're going to describe these three in context with solute, solvent, and solution. So these are the types of solutions that we're going to need to know for our next part of our unit. So let's start with the isotonic. Iso means same. Okay, so this is going to be a solution that is going to be the same amount of solute on both sides. So the before is the same solute on both sides. So then the after we will describe in a second, but I'm going to go ahead and draw some dots, 3 dots. And I'm going to say the same amount of solute on both sides. So let's go ahead and put the solute on the outside in some water, some solvent, we call it. Okay, so we have this cell, it's got 3 particles of solute. All right. And our outside has some solvent, some water, and we've got 3 particles of solute as well. So what is going to happen to the cell? Well, with isotonic solution, the water will move across equally. So let's go ahead and draw our arrow of water moving across, and the arrow is going to show the same length. So you're going to write in your um, after, I don't remember what color I used. Here it is. That the water moves across equally. So then you can ask what happens to the cell. The cell remains the same size. Okay. So if I was going to quantify this in a percentage, I could say that this is 30% solute on the outside and 30% solute on the inside. So if I have the same amount of solute on both sides, well, I always got to add them up to 100% on each side. So 30% solute and 70% solvent, which is the water. Okay, I want to add this to our studies here. Let me move this solute particle over here. Okay, so the solvent is water. So I just want to remind you. Okay, so when you're analyzing this, I always tell the kids to look at the solute number. It's just easier. Okay, and water moves towards the larger solute. Well, in this case, the solute number is the same on both sides, on the inside of the cell and the outside of the cell. So in this case, water will move equally across the membrane. Okay. So next one is hypotonic. I like to think hypo like a hippo. Hypo means that the cell will swell like a hippo. And you can see this hippo, he's so cute. Okay, so the before, let's go ahead and write the before. The cell is put in, the cell or the solute. There's more solute on the outside. Oh, I'm so sorry. Inside of the cell. So let's go ahead and make that happen. Let's put some dots in there. Let's put like, I don't know, 8. Under 4. Doesn't really matter. I don't care how many dots you put, just lots of dots. The dots mean solute. And then on the outside, we are going to draw the solution we're putting it into, and then we're going to draw the dots on the outside. Don't write as many. Okay, so the after is the water is going to go towards the side where there are more solute particles. So if I was going to quantify this, okay, I would say that there are, I don't know, 90% solute on the inside and 20% solute on the outside. So then you fill in your solvent number. You just do 100 minus the number, so 80% solvent, also known as water, and this is 10% solvent. Okay, but what we really care about is the solute number. So the solute number is higher on the inside. So your arrow is going to be massive going in, like this. And then a little bit of the water is still coming out, okay? But most of it's going in. So then you can say the water rushes in, okay? And the cell will bloat or swell up like a hippo, hypotonic solution. So the cell is in this solution and it is going to be uh you know swelling up, and so this is because there is more solute in the cell when you put it in the solution, so then the water is going to go to rescue the cell, I like to say. All right, lastly, hypertonic, I like to say that this is going to be the cell shrinks like a small little child, hyper little child. So it's a smaller cell. Okay, so the before on this one is the solute is greater on the outside or in the solvent. The after, we're gonna take a look at right now. So let's go ahead and do our solution once again. Draw your water, draw all the solute on the outside. Woo hoo. Just lots of dots here to show the solute is more potent on the outside and the inside is not as much. So then if I want to quantify this, you can put a percentage on here too. You could say, I don't know, 3% solute and 85% solute. I don't know. I'm just making this up. So then you do 100 minus that to get your percentage. So 15% solvent on the outside and 97% solvent on the inside. So wherever your solute is greater, the water will rush to that. So let's go ahead and make your water arrow very big leaving and a little bit going in because there's still some water coming inside the cell, but not as much. Okay, so the after is that the water will rush out of the cell and the cell will shrink. Okay, and that's about it for these 3 types of solutions that you could have based on your solute and solvent numbers. Here are some examples of animal cell versus plant cell. So in a hypertonic solution, the cell will shrivel or shrink. In a plant cell, we call it plasmolyzed. In an isotonic solution, it is normal for an animal cell to be isotonic, and it's also known as flaccid in a plant cell. And the hypotonic hippo, larger, it becomes so large that the cell is so large it could burst in an animal cell. And in a plant cell, we call it turgid. Okay, so what I want you to do right now is I want you to go ahead and practice. I want you to read these statements and check off if you believe they are hypotonic, isotonic, or hypertonic. Thanks for watching.